All right, so last class we talked about three major parts of the periodic table, three major sections of the periodic table in metals, nonmetals, and metalloids. And so today we're going to go even more in detail about different parts of the periodic table and start talking about groups. Okay, groups, if you remember, are the things that go up and down on your periodic table. So groups go up and down. And there are 18 groups on the periodic table. And so I would like for you to take out your periodic table and label the group numbers just like they are here. So group 5 are these elements, group 6 are these elements, 7. We label them all the way 1 through 18. So grab your periodic table and get them out and label them 1 through 18 so that when I reference these elements in group 18, you know that I'm talking about this column or this group of elements right here. So now that you've got them labeled, I want to talk about a few of the groups. We're not going to go through all 18, but I want to talk about a few of the groups and some characteristics that they have. So we're going to start with group 1, which is the group farthest to the left on the periodic table. So it is called the alkali metals. All right, group 1 is called the alkali metals. They include all the elements lithium, sodium, potassium, rubidium, cesium, and francium. You will notice that just because hydrogen is in group 1 does not mean it is considered an alkali metal. Okay, and that is because hydrogen is not a metal at all. It's a nonmetal, right? It only sits in group 1 because of the number of electrons it has. So we'll talk about that a little bit as we go on, but it's important to understand that the alkali metals really is this group, but it does not include hydrogen. Okay, so hydrogen is kind of on its own, right? It sits in group 1, but it is not a metal, and so it is not considered a part of the alkali metals group. Okay, so anyway, that's group 1. Some things we need to know about group 1 is that they have a silvery, kind of shiny appearance, and they are very, very soft. So soft we can even cut these metals with like a butter knife or a dull knife. It's kind of the consistency like of softened butter. That's kind of what these metals consist of. These metals are not found in nature. Okay, if I was walking through the forest or down the street or whatever, I would not find a chunk of sodium metal sitting there, or lithium metal, or potassium, any of these metals sitting there, because they are so reactive. They are too reactive. They don't want to exist on their own. They would rather exist as a part of a compound. They would rather exist bonded to something else. And so they are too reactive to be found in nature. Mostly they're too reactive with water. They are especially reactive with water. They will burn very quickly when they react with water. Some of them even burn so quickly and so hot that it causes an explosion, right? But they are too reactive. So if that was the case, if we had these metals in free, kind of in nature, there's water everywhere around, right? So they would constantly be burning, constantly be bonding with things. So they wouldn't stay by themselves for long anyway. Okay. The thing I want you to remember about group 1 is that they have only one valence electron. All right, and we talked a little bit about what valence electrons are, but let's remember again here. Valence electrons, they are electrons in the outermost shell of an atom. These are, or otherwise, kind of you can think of them as they're electrons available for bonding. Okay, so if these metals only have one valence electron, I want to kind of readdress here what atoms want. They want to have a full shell of electrons. And if I'm drawing some pretend atom here, let me just draw sodium, for example. Sodium has 11 total electrons, 2 in its innermost shell. Then the next shell has 8, 1, 2, 3, 4, 5, 6, 7, 8. And then its outermost shell only has 1. So that adds up to 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So we've got 11 electrons in sodium. 1 in the outermost shell. So this is its valence electron right there. Now, what atoms want to have is they want to have a full shell of electrons. And a full shell means 8 electrons. Okay, so this second shell right here for sodium is full because it has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And so what we have to think about with sodium and with all of these group 1 elements that only have 1 valence electron, is it easier for them to gather 7 more, right? 1, 2, 3, 4, 5, 6, 7. Or is it easier for them to just give away that single electron they have in their outermost shell, leaving them with a full secondary shell? Well, the answer is that it's easier for them to give away that 1 electron. And so that's why they're so reactive. They only have 1 electron that they need to get rid of before they can have a full shell and before they can be happy, right? That's what makes them happy, is to have that full shell. So if they only have 1 to give away before they get to that full shell, that means they're really easy to bond with. All right, so group 1 has 1 valence electron, and that's what makes them so reactive. They want to bond with other atoms. So moving on to group 2, these are called the alkaline earth metals. They involve all elements in group 2. Okay, so here's my periodic table again. These elements in group 2 all are considered alkaline earth metals. Okay, we're moving from the left to the right. So we already talked about the alkali metals in group 1. Now we're looking at group 2, the alkaline earth metals. These are a little bit more dense, a little bit stronger than the alkali metals. So as we move from group 1 to group 2, these metals start to take on more characteristics of what we consider to be regular metals, right? They're a little stronger, a little tougher, a little harder than alkali metals. They have higher melting points, so it takes a little bit more heat for them to go from a solid to a liquid. They are less reactive than the alkali metals. However, they're still too reactive to be found in nature. Okay, the same type of rule applies here. They are still too reactive to be found in nature. They would bond with too many things to be left alone, so they would rather be bonded with something. Okay, now I want you to see here that group 2 elements all have 2 valence electrons. And remember, valence electrons are outer shell electrons, right? They have 2 of them. Group 1 has 1 valence electron. Every element in group 1 has 1 valence electron. Every element in group 2 has 2 valence electrons. We are going to see that pattern continue, okay? In a sort of in a roundabout way here. I'll show you in a minute, but group 2 has 2 valence electrons. And so if we're talking about the outer shell of some atom having 2 valence electrons, is it easier for them to gather 6 to get the 8 they want? Or is it easier for them to give away their 2? Well, it's easier for them to give away 2 to leave them with a full inner shell. So they're still extremely reactive. So next we move to the middle section of the periodic table called the transition metals. The transition metals. These are groups 3 through 12. So if we look at the periodic table again, and you don't need to be labeling the names on your periodic table. What you need to have is the group numbers. Okay, so don't be labeling on your periodic table the names of the groups. Just make sure you have the numbers of the groups labeled, like I asked you to do at the beginning. So group 1, group 2, 3, all the way through 12, and then 13 all the way through 18, right? We want to have all those groups labeled there. But these are the transition metals right here. Groups 3 through 12, it's the smaller chunk in the middle of the periodic table that is considered the transition metals. They have very typical metal properties or metallic properties, things that we listed earlier, like they're malleable, they are have high tensile strength, good conductors, all of these things we talked about earlier, they have them. And a lot of the metals that we think about when we say the word metal are found in the transition metals, things like zinc, copper, gold, silver, mercury, all these metals that we think about are found in the transition metals section of the periodic table. So here are some typical metallic properties we talked about earlier. We need to know that they are less reactive than the alkali metals or the alkaline earth metals, so then group 1 or group 2, and they do exist as a free element, which means they can exist on their own without being bonded to something. Okay, they do actually exist in nature as free elements. Okay, there's a couple more metallic properties there. Remember, if we look at the word ductile, that means it can be pulled into a wire, right? And malleable means we can pound it into thin sheets. Okay, the thing that is different about these groups on the periodic table is that they don't follow the rules or the pattern for valence electrons. So it is not true that every element in group 3 has 3 valence electrons and every element in group 11 has 11 valence electrons. That is not true. So they don't follow the pattern. The pattern will pick back up when we get to boron's group, and we'll talk about that here in just a little bit. But they have a variety of valence electrons, and so there's no real discernible pattern for valence electrons within that bunch of transition metals. All right, we're going to skip over now on the periodic table all the way to group 17 called the halogens. Okay, called the halogens. Before we get too much into the halogens though, I want to talk a little bit about the patterns of valence electrons on the periodic table. So we said group 1 elements all have 1 valence electron. Okay, that's how I'll abbreviate valence electrons, is valence electrons, right? Group 2 all has 2 valence electrons. We said the transition metals don't follow the pattern associated with valence electrons, which is true. But when we get to group 13, right here, this is group 13, these elements all have 3 valence electrons. When we get to group 14, these elements all have 4 valence electron. At group 15, these elements all have 5 valence electrons. At group 16, these elements all have 6 valence electrons. 17, these elements all have 7 valence electrons. Do you see the pattern there? So we don't have 13 valence electrons, but we do have 3. We don't have 14, but we do have 4, right? We take 10 away from their group number to tell how many valence electrons they have. And so that means group 18 then has 8 valence electrons, which means all of these elements already have exactly what they want. They already have the 8 electrons in their outer shell that they want to have. Okay, so we're going to look at that here in a little while, but I want you to notice the pattern for valence electrons on the periodic table. We skip over the transition metals and we go 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. Okay, so we can get all the way to the end of the periodic table until we get a full shell. All right, so let's go back to the halogens now. The halogens are group 17. So way over here on the right-hand side. Way over here on the right-hand side, right there, fluorine, chlorine, bromine, iodine, astatine, And what's the last one? Oh, I can't see it on this one. Okay, that's the last of our halogens right there. The other one is a metal, but these are group 17 elements. They are the most reactive group of non-metals. So the most reactive group of metals was group 1. The most reactive group of non-metals is the halogens. They can be either gas, liquid, or solid at room temperature. And the reason that they are so reactive is because they have 7 valence electrons. And so I want you to think about this. If I'm looking at the electrons in their outer shell and they have 7, 1, 2, 3, 4, 5, 6, 7, how many more do they need to get a full shell? They only need 1 more electron. And they can take that electron from any element that will give it away. So it's really easy for them to get that full shell of 8 electrons, right? That's what they want. And so to get 8, they only need 1 more, which is why they are so reactive, right? They're able to take that electron from a lot of different things, which makes them really, really reactive. Okay, usually they are too reactive to be found in nature, just like the group 1 and group 2 elements we talked about earlier. Okay, these guys are not reactive with water, unlike group 1 elements. All right, and the last group specifically we're going to talk about is called the noble gases. They are in group 18. They are extremely unreactive, and I want to see if we can figure out why. So here's our periodic table again. Group 18 is all the way over here on the right-hand side. This is group 18. And if you remember, we said they had 8 valence electrons. So why would they be unreactive, right? Why would they not want to bond with other elements? Well, the truth is they already have a full shell. They already have 8 valence electrons. So there's no need for them to go grab an electron from another atom and bond because they're already full, right? It's just not necessary for them to bond because they already have exactly what they want. So that means they're generally unreactive, right? They're okay just hanging out by themselves. All of these are gases at room temperature, right? Hence the name noble gases. They have full outer shells, which we already said contain how many electrons? 8. Okay, they contain 8 electrons. So full outer shells equals 8 valence electrons. Okay, all of these noble gases are used in what we consider neon lights, right? We call them neon lights, but realistically, they all contribute to neon lighting. So different colors of neon lights come from using different gases and a mixture of different gases, but they're not all just pure neon. So it's kind of interesting. Okay. Last 2 parts of the periodic table I want to talk about is something called the lanthanides and the actinides. The lanthanides are shiny metals. They act very similar to the group 2 metals. The actinides are right underneath of them, and they are all what we call radioactive. So they decay really quickly, or sometimes not that quickly, but they are radioactive, which means they're kind of dangerous to be around. Some of them are found naturally on Earth, and some of them are man-made, which means they were produced in a lab. Both of these groups are placed below the periodic table to save space. So let me show you where the lanthanides and the actinides are. The lanthanide series, they're called lanthanide series, is this row of elements right here. It starts with the element lanthanum. That's why they're called the lanthanide series. And all of these elements right here are considered to be part of the lanthanides. The actinides start with actinium right here, and they include all of these elements. So the lanthanides and the actinides sit below the periodic table. Where they fit in the periodic table, however, is right here. The lanthanides and the actinides would sit right here on the periodic table. From here are the lanthanides, Here are the actinides. The reason they move them below the periodic table is just to save space. So if we didn't have them separated down below, this is what the periodic table would look like. So it's a little more crowded, kind of hard to see, but that's where they go in terms of their proton numbers. So right after 56 is lanthanum, which is 57, all the way through 70. And then actinium starts on 89 and goes all the way to 102. But that's where they would fit on the periodic table if we wanted them to sit in the same spot. So we pull them below just to save some space, and I'll show you what that looks like in comparison. So there's what it could look like. But again, this is what our periodic table does currently look like. We put the lanthanides and the actinides right down here just to save some space.